Hi, my name is Aaron Sampson. What goes on under the hood of computers is a marvel of human ingenuity that most people don't stop to consider in their day-to-day activities, even though computers are never far away in both our professional and private lives. In this course, I'll introduce the basics of data, CPUs, and troubleshooting, beginning with an overview of data and information as assets, intellectual property and digital products, and data-driven business decisions. Then I'll explore processors, data storage measurements, and throughput measurements. Finally, you'll be introduced to troubleshooting, including the methodology used for preventing, detecting, and remediating problems. Upon completion, you'll have built the foundation for the basics of IT. This course helps to prepare learners for the CompTIA IT Fundamentals or ITF Plus certification exam, FC0 U61. In this presentation, we'll examine how data can be regarded as an asset in the modern business world. And in fact, in some cases, it might be the most valuable asset to an organization. So, as an asset, data can be bought or sold like anything else, but it can be difficult in some cases because it's not something that's tangible, in that there's no set price tag or even a generally accepted rule as how to apply a value to data. Most notably because any given data set might be extremely valuable to one organization, but that same data might not have any value at all to a different organization. And with respect to obtaining data in the first place, while it might be particularly valuable to an organization, it might not cost anything to acquire it. Data can come from just about any source, and in today's world of social media posts, online videos, and podcasts, and anything else that's generally available online, data sources are just about endless. But while obtaining valuable information might not cost anything in some cases, that data has to then be managed, which typically involves filtering out what is useful, storing it in some kind of repository, analyzing it for the most pertinent content, replicating it to other internal locations, securing it, backing it up, and many other processes to ensure that it can be useful to the organization. So even if it is obtained for free, there can still be tremendous costs associated with its management. So organizations still need to be mindful of the return on investment, or ROI, to ensure that the efforts and the resources required to manage that data are in fact providing a return to the organization. And in short, if all of that effort yields no tangible results, then the investment isn't worth it. Something else to be mindful of when dealing with data are the terms of data versus information. You might hear these terms used somewhat interchangeably in day-to-day conversation, but in the strictest sense, they aren't the same thing. In short, data can be thought of as raw or individual facts, whereas information is the organization and analysis of those facts to create something more meaningful in the larger picture, so to speak. A common example in business environments is the use of databases and a process generally referred to as data mining. A database might store individual records of something like product sales, so you could look at any given record, and you might discover that any given customer purchased any given product. Now, that might be useful to know, but if you're wondering which products are the top sellers, in which regions, or for which demographics, or under what circumstances, or which factors tend to influence a customer's decision to purchase that product in the first place, individual records do not provide this kind of information. So the data must be gathered into much larger groups for starters, and then examined and analyzed much more closely to produce those results, which might then indicate that a particular product is not selling as well as you thought, perhaps in a certain region or to a particular demographic group. So you can now focus your efforts on marketing and advertising to boost sales where needed. So that raw data, which has now provided you with much more useful information, can help an organization to understand the value of their data and to embrace a data-based culture, and to acquire the information necessary to make better business decisions. In fact, that overall process of data mining is also often referred to as decision support, because it can help to indicate where more attention is needed within your organization. But coming back to the return on investment, processes such as data mining can be very resource intensive, so understanding the value of your data still has to involve considerations such as how that value is measured. For example, does it actually yield more profit, such as through increased sales, or perhaps does it yield a broader customer base? And since data is so plentiful in some cases, you have to have the ability to identify which data is valuable and which data isn't. Plus, the lifespan of that data should also be considered, because some data might only be valuable for a very short time, whereas other data might be useful for a very long time. So, given all of those factors, an organization needs to establish some kind of strategy that can help to quantify the value of data and determine the investment and costs associated with its maintenance and management, and determine the overall level of usability for that data to help them determine exactly which data is valuable and which data isn't. These processes are often referred to as data cleansing, which essentially means that you aren't wasting time and effort chasing down data that won't yield any results. Now, those processes themselves will vary depending on the organization, but ultimately, the goal is to ensure that the data you're working with is appropriate and meaningful to your business. In this video, we'll provide an overview of intellectual property as an asset, which, very much like data, is regarded as an intangible asset because, again, in many cases it can be difficult to put a price tag on it, so to speak, but it's nonetheless often very valuable to an organization or an individual. That said, intellectual property can take many forms as compared to something like data, because intellectual property encompasses things like inventions or new technologies, new brands, new software, processes, and or designs, or really any new idea. So it can be regarded as somewhat more tangible than data. For instance, if you've developed something like a new type of physical device, it might not be immediately obvious what that device is going to be worth, but you might at least have a very good idea of what it costs you to construct. But like any other asset, how you use your intellectual property is of critical importance to your organization. So not only do you need to develop a strategy for its implementation, you also need to ensure that it remains protected, because if lost or stolen, you could completely lose your competitive advantage in the marketplace, especially if that property has the potential to generate significant earnings. So with respect to protecting intellectual property, there are certainly methods that you can employ, such as patents, which are government-issued rights that protect your IP to ensure that you're able to develop and market your idea, product, or service, but more importantly, to ensure that no one else can. Now, that said, you should be mindful that patents usually have an expiry date, after which others are able to copy and reproduce whatever was originally patented. And there are also various requirements that must be satisfied before a patent can be issued, which can be time-consuming, of course, so the earlier you begin the process, the better. Trademarks can also help to protect your IP by using specific words, symbols, designs, or sounds that uniquely identify the goods or services of your organization. In short, they help customers to identify and distinguish your organization in the marketplace. Now, in some cases, a trademark can be obtained simply by using it, provided, of course, that it's something unique. For example, if I want to start a fast food chain, clearly I can't use the trademark of an existing one. But as long as it's something that I've developed on my own, and that it is not in conflict with any others, then it can be considered to be a trademark. But of course, you can make it more official, so to speak, by applying to an appropriate entity for your region. For example, in the United States, you can apply to the United States Patents and Trademark Office, who can then register your trademark to ensure that no one else can use it. Provided your application is approved, then you might often see a small TM next to your trademark, which of course stands for trademark, or the letter R inside of a small circle, which indicates a registered trademark. A copyright is another method to protect intellectual property by giving you the right to produce, or perhaps more accurately, reproduce or copy a piece of work. But they're a little more specific than something like a trademark or a patent, in that a copyright only applies to some kind of expression, such as literary, artistic, or musical works. But again, as the name indicates, a copyright gives you, and only you, the right to copy or reproduce it, disseminate it, and ideally to profit from it. Industrial designs can be registered as well to help protect your IP, specifically with respect to a product's appearance in terms of overall shape, pattern, or ornamentation. Now, in some cases, these aspects can be rather difficult to uniquely distinguish, so the more distinct those features are, the more likely they are to be recognized, and the more likely it will be that you'll be able to register that design so that no one else can use it. Lastly, perhaps the least formal method of protecting intellectual property is the trade secret, which can be defined as simply any information that an organization wants to keep private. Common examples might be a secret recipe for a restaurant's signature item or a chemical formula for a product. While official means of protection aren't as common, it doesn't mean that the trade secret is any less valuable to the organization, so in many cases, the method of protection might just be through internal policies and procedures, non-disclosure agreements, or simply treating the trade secret as valid grounds for dismissal if it's discovered that someone divulged that information to a competitor or to the general public. Now, that all said, you can still apply to register a trade secret, but the specifics and the requirements will vary based on your region. So be sure to investigate if you feel it's something that might help to protect your IP. In short, if you have anything that you feel qualifies as intellectual property, then it should be regarded as an asset that is or can be as valuable as any other, if not more so. Again, in some cases, IP is the sole basis of the business, so be sure to implement whatever measures are necessary and appropriate to ensure that property is not lost or compromised. In this video, we'll outline the basic characteristics of digital products, which quite simply are exactly as their name indicates, products that are created and deliverable through electronic means such as downloading from the internet or distributed on some kind of physical media such as DVDs. Now, we'll take a look at some more extensive examples in just a moment, but common digital products include music, ebooks, software, and movies and TV. So if you've ever even gone onto a website such as YouTube and watched a video, as I'm sure you have already consumed a digital product. So, as mentioned, one of the most common ways to access digital products is to simply download them from the internet, in which case they don't have any physical form. You just go to the appropriate website and either download your own copy or you just stream it on demand. But digital products can still be purchased from traditional brick and mortar locations. For example, an office supply store would almost certainly still sell business software off the shelf, wherein you purchase the physical media, such as a CD or a DVD, and you install it locally on your devices. Now, digital products have a number of characteristics that make them attractive as a business model, perhaps most notably the fact that they're very easy to modify. Now, this might not apply to all forms of digital media, but consider something like a line of business software application. As a developer, you will almost certainly make improvements over time and ultimately release a new version. Well, that new version only needs to be updated once in what you might consider to be the master copy. With that done, all new downloads of that product will be the newly updated version, whether it's one customer downloading it or a million. So compare that to some types of physical objects, such as a recall on a faulty part for a vehicle. Not only would you have to manufacture possibly millions of that new part, they all have to be installed on all vehicles that contain the original faulty part, which could represent a tremendous cost for the organization, as consumers almost never have to pay for a recall. But let's say if a glitch is discovered in a software application, the developer need only create a single copy of the fix, and in most cases, the software can apply it itself and automatically through its regularly scheduled update service, no matter how many instances there are. So by simply creating that single copy of the fix, you can correct every instance that is out there in the public marketplace. In addition, digital products typically require a license or a subscription for their use, but you still only have to create a single instance. So again, compared to a physical item where you would have to manufacture a new one for each person who wants one, with digital products, consumers are all paying separately for what is effectively the exact same product. Those and other characteristics provide many businesses advantages as well. Digital products are not only very versatile in what they can do, but also in how you implement them. For example, they might be your primary source of revenue if you're selling a particular digital product, but they can also be used to increase awareness for other products. For example, you might distribute various tools and utilities for free to increase awareness of your primary brand and/or product. This worked especially well for Adobe, who has offered their Reader application for free for decades, resulting in them becoming almost a ubiquitous name for other products that are sold separately, such as Photoshop. Digital products are extremely cost-effective as well because there are far fewer management and overhead costs associated with them. For example, at least for content that is only downloaded or streamed, you don't need any physical space to store them. There are no concerns for inventory nor for packaging and shipping, all of which can lead to significantly higher profit margins because you're simply spending far less to do business. So coming back to some other types of digital content, they might include memberships to various online services where members gain exclusive access to content that is not otherwise available to the general public. For example, special interest groups, how-to or educational sites, fitness and nutrition sites, or travel and leisure services. Podcasts are online audio broadcasts that are available to be streamed or downloaded and include topics from just about every aspect of daily life. Tools and utilities that could assist with any aspect of business, such as streamlining your business processes or providing assistance and guidance with launching a new product, or services such as legal counsel, accounting advice, or medical consults. More specific products might include software applications ranging from enterprise-level business applications through to free apps, widgets, and plugins, ebooks for digital readers, music and entertainment services such as Spotify or iTunes. Perhaps the most well-known examples such as Netflix, Amazon Prime Video, or YouTube for streaming videos, movies, and TV shows, coaching and training services, and templates for building your own digital products such as websites or presentations. So, regardless of what kind of digital content you're working with, digital products have many benefits that can offer tremendous advantages as a business model if you're a provider, and many benefits to the consumers as well, because all we need to consume them is some kind of computing device. And of course, since most digital products are obtained online, we can access them from anywhere, at any time, and from any device as long as we have access to the internet. In this presentation, we'll identify the characteristics of data-driven decision-making, which is a process that is pretty much given away by its name. Rather than making business decisions based on hunches or simply what those who make decisions want to do, hard data is used to guide the strategic decisions with respect to the direction of the organization. By doing so, you can champion an organizational culture that encourages critical thinking, not only for the highest level decision makers, but for all employees throughout all of their daily activities. In short, you act based on what the data is telling you. For instance, if data clearly indicates that a particular product simply isn't selling no matter what measures you've taken, then it makes more sense to discontinue that product rather than to continue directing resources into boosting its sales. Now, that's obviously a very simple example, and even the process itself sounds easy enough. But the issue with making data-driven decisions can be the process of capturing and gathering the data in the first place and ensuring that it can be converted into a usable format that provides meaningful information. These days, there are various processes and applications that can be used to do this, but the challenge with making data-driven decisions can sometimes be understanding exactly what the data is telling you. So you'll need to ensure that appropriate methods and processes are in place to turn that data into information so that it can be used to properly support your decisions. So one of the first decisions then is how you want to approach the process of capturing data. And at the most fundamental level, there are two basic choices: manually or through automated processes. Now, to clarify, manually in this context would typically mean through the use of internal databases that involve the entry of records by your employees. For example, if your organization is in sales, then whenever a sale is made, there is likely a salesperson who generates some kind of an order form and or an invoice, which is then stored in a central database. So those records will, of course, accumulate over time. So that data can then be used as the source for data analysis to generate useful information. So again, manual in this context doesn't mean that there aren't applications and database services in place. It just means that data is initially entered by your own employees. However, if the data sources you rely on are very large and or the data effectively generates itself, then you might need automated processes to capture what is needed. An example of this might be an organization that offers marketing and advertising solutions to other organizations to help them create more targeted ads. Their data source might be to examine social media sites to capture trending data to help them discover which companies should advertise which products to which people. So the data itself in this case is being generated on its own, so to speak, because of course it's all being entered by those who are making the posts. But the volume of data that needs to be captured in such a case would be exceptionally high. So automated processes would have to be used to capture the relevant data. But capturing the data is only the first part of the equation. In order to make decisions based on that data, there needs to be a correlation or an association between the data and the decisions that will be made based on that data. So this is where data analysis comes into play. It identifies any unrealized relationships within the data that can help to indicate what the data is actually telling you. Now, just to quickly clarify, the term relationships when it comes to databases and various other sources of information can have different connotations. In the manual entry sales database that I mentioned earlier, those types of databases are often referred to as relational databases because data in one table is related to data in another table. For example, one table would store your customer information, but any given customer would place orders, and those orders would then be stored in a separate table. So there is a relationship between the tables wherein any given order can be traced back to the customer who placed it simply by entering some kind of identifying value such as the customer ID on the order. So when a new order is generated, let's just say it's order number 1000, one of the first values that is entered into this new order is the customer who is placing it. Let's just say it was customer 100. So the fact that the order references the customer number is what's known as the relationship between those tables, because I can use that customer number of 100 to retrieve all of the customer information if I need to. But that's not what a relationship means in terms of data analysis. Knowing that any given order was placed by a particular customer doesn't tell you much in terms of trying to make a business decision. But knowing that all sales of a particular product tends to increase under certain conditions can be very useful. Now, this is a very simple example purely to illustrate the point, but imagine you owned a sporting goods store in an area where you experience all four seasons. Clearly, you would know that you should increase the stock of things like bicycles and water sports items as summer approaches. And conversely, as winter approaches, you would increase the stock of skates and skis. Again, this is obvious, but it's the fact that the weather has an effect on which products will sell better that is of interest here, which is not something that is directly stored in a database. Any given order would certainly have an order date on it, but it would be very unlikely that you would see a value on an order that specifically states that it was placed in the summer or the winter. But the point is that there is a relationship between the seasons and the products that sell better. So this is what data analysis attempts to uncover: various connections or relationships that might not be immediately evident, but can certainly affect your organization. So with those processes in place, when it comes to making the actual decisions that will affect your organization, the overall process should involve ensuring that you're able to determine the key questions and business objectives that are appropriate to the circumstances. You should verify that you have gathered and cleansed all appropriate data, and in this context, cleansing means that you have filtered out irrelevant or erroneous data. Then determine the insights that can be ascertained from that data through data analysis, which should indicate which actions should be taken. Then synthesize that information into meaningful reports that can be used as clear justification for taking any given action. As for the reporting aspect, this is effectively the final stage of decision making, and reports also represent the results of your data analysis processes. At its core, reporting is the conversion of raw data into useful information that is then presented in a clear and easily understood format that summarizes the correlations and relationships discovered by your analysis, making it easy to provide any answers to the questions of the decision makers. And those answers will be based on data and facts, not opinion. So just quickly coming back to my very simple example of the sporting goods store, a proper analysis and report should clearly indicate that as the temperature increases as summer approaches, bicycle sales increase at a commensurate rate. So a decision to stock more bicycles in the spring is entirely backed up by the data. Ultimately, organizations should strive to make data-driven decisions the norm, if for no other reason than to reduce guesswork as much as possible. And none of this is to suggest that there won't still be some situations where the data simply isn't clear enough to make a solid decision, but by normalizing this approach, you can at least provide justification for decisions that were made based on the data, which in turn can help to increase the comfort and confidence level of your employees, while also helping to ensure that customers and stakeholders are satisfied with the direction of the business. In this video, we'll take a look at the basic characteristics of a computer's central processing unit, or CPU. Now, the CPU can really be thought of as the central or the main computer processor, and quite literally is the central control chip of a computer. And a good analogy really is to think of it as the computer's brain. It handles all of the actual processing with respect to all data that comes in and all data that is sent out. In short, almost everything has to interact with the processor to some degree when it comes to computing. Now, there are a number of different tasks that are performed by the CPU, but again, in short, its job is to execute computer instructions. Now, those instructions come from the programming within an application or a service, but in general, they include tasks such as logic operations, math, and handling input and output. Now, logic tends to refer to scenarios, such as what should be done if a particular condition is true or if a particular condition is false. So it might follow a flow chart or some sort of hierarchy. That's what's referred to as logic operations. Math is exactly as it sounds. So if, for example, you were working in a spreadsheet and you needed to calculate the sum or the average of a range of values, the processor does that math. Input-output refers to any and all data that is received into the processor from the computer's memory and all of the processed results that are written out to the computer's memory. And that overall process is typically referred to as I/O. So to perform all of those different operations, there are several different components to a CPU, including the control unit, or the CU, the arithmetic logic unit, or ALU, registers, a clock, a small cache of memory, and what are known as buses. Now, the control unit essentially controls the flow of data. So coming back to I/O, it ensures that all of the input, is processed accordingly, and that the processed information is sent as O, or output. So you can think of it as controlling the flow of traffic. The arithmetic logic unit, again, does exactly as its name indicates. It's the component that is responsible for mathematical operations. Registers are small, fast storage locations that are available to the CPU to hold an instruction or an operand until any given instruction can be fully completed. For example, an instruction might be that the contents of one register should be added to the contents of another register, with the answer placed into a third register if further processing on that value is required. And the size of any given register will typically match the architecture of the processor. For example, in a 32-bit processor, each register will be 32 bits in length, and on a 64-bit processor, each will be 64 bits. The clock refers to a cyclical value that determines how quickly instructions can be accessed, and we'll talk about that in greater detail in just a moment. The cache is a small amount of memory built right into the processor itself that can temporarily hold processed data until all of the data is ready to be written back to memory, and buses refer to the actual pathways between the processor and the system's memory. Now, as for the modern CPUs that are available on today's market, you will often hear them referred to as multi-core CPUs, which quite literally means that they contain multiple cores. In earlier versions of processors, there was only a single processing core in a single physical chip. More advanced systems could support multiple physical chips, but now what we have is still a single physical chip that literally contains inside of it multiple processing cores, and each core is able to focus on a different task. So what you get from a multi-core processor is the ability to quite literally multitask. And in this context, it does literally mean that more than one process can be processed at the same time. So almost every processor these days is a multi-core processor, but it comes down to how many cores there are. You might see a dual core, a quad core, and so on. And in fact, it wouldn't be unusual these days to see as many as 16 cores on any given processor. It will depend on the type of system itself. But in short, the more cores you have, the greater the processing power you'll have. And in addition, any individual core can also implement a process known as multi-threading, or sometimes also referred to as hyper-threading, which creates virtual cores. Now, this is not the same as having a separate core, but any individual core, as mentioned, can accept more than one set of instructions at the same time. Now, it cannot actually work on each thread at the same time, but what it can do is take turns. So let's just say that two threads or two sets of instructions are being fed into the processor. It will accept both of them. It will work on one, then it will take a break, for lack of a better word, and work on the other, and it will keep switching back and forth until both sets of instructions have been processed. So this does actually still create additional processing power and creates what's known as virtual cores. So what you end up with is the single physical chip, and just for easy math, let's just say it has two cores. So now we have two cores within that single physical chip, but if each core can accept two threads at the same time, then you effectively have four virtual processors, because again, there are two cores, but each core can accept two sets of instructions. So in total, you have four virtual processors in that system. Now, we touched on the clock speed earlier, which again is a speed that is measured in cycles per second, and we'll take a look at those in just a moment as well. But it's the speed at which the CPU can access and process instructions. And these days, on most processors, those cycles are measured in gigahertz, which means 1 billion cycles per second. Now, if we go back a little bit and just look at all of the available clock speeds, 1 cycle per second is measured in 1 hertz. Now, that would be very, very slow, of course. That is only a single cycle per second, but the frequencies are typically incremented in units of 1,000. So 1,000 cycles per second is a kilohertz. Then we get up into the megahertz values, which is 1 million cycles per second. Now, when I began my career in IT, these were the values that we were seeing. And in fact, they were low in the megahertz range. For example, a 10 or a 20 megahertz system was actually fairly common when I began. And some of the earlier systems, going back even before I began my career, were measured in values as low as 4 or 8 megahertz. But again, around 20-ish was common when I began. Now, they certainly started to get faster very rapidly, and by the late 1990s, I would say, we were starting to see processors in the gigahertz range, and they are still fairly low in the gigahertz range. In other words, it's not at all uncommon even these days to see a processor that might only be between 1 and 2.5 gigahertz, but that's not to indicate that we've sort of stalled, because again, what you also have now are multiple processing cores that can all operate at those speeds. So we get much more processing power without having to increase the speed too much. And the reason why the speeds aren't just going up faster and faster all the time is because the faster they go, the hotter they get, and you have to consider cooling. CPUs would get very, very hot if they were not adequately cooled. Now, you might still hear the values of terahertz, which is a trillion cycles per second, petahertz, which is a quadrillion, and even exahertz, which is a quintillion. But those values really aren't seen in processors today. But that's not to suggest that they won't show up eventually. So again, for today's systems, something in the low gigahertz range is certainly very common and very acceptable and very capable of processing a lot of information. But as mentioned, the speed is not the only consideration, but neither is the number of processing cores. In other words, neither one is an absolute measure of the CPU's power. They each rely on the other, and both should be taken into consideration, particularly when you're considering a new purchase. Now, ideally, if you have multiple cores that are as fast as they can be, then you're going to have a much more powerful processor, but of course that would cost more. So it really just comes down to budgetary constraints and what you feel is an adequate level of performance. But like I just said, if there are multiple cores and they are all running at their maximum speed, that will clearly be the most powerful system. But of course, it also depends on what you need it for. In other words, if you're just looking for a home computer on which you will just do casual internet browsing and emailing and some general applications, you just don't need that kind of power, so you're spending money for nothing. However, enthusiast level systems such as gaming computers and of course business systems that are dedicated to very complex tasks do need that kind of processing power, but in those cases, budget might be a little less of a concern. So again, it's all about balancing all of the appropriate factors, but ultimately you should consider every aspect of a processor when it comes to which one is best suited to your needs. In this video, we'll take a look at the various measurement units that are used with computer storage. Now, this ultimately begins with the single bit, which in fact is a contraction for binary digit, meaning that it is either a 1 or a 0. So if it's a 0, it's treated as off in terms of the value. If it's a 1, it's treated as on. And again, I've mentioned this before, but a good way to think of this is a simple light switch. It has two options and only two options. It is either on or off. In other words, there's no in between. There's no gray area or half value. It is either one or the other. Now, even though that is the smallest value that can be used in computing, it typically does not mean much for most applications. So 8 bits are put together to form 1 byte. And 1 byte in one of the most common encoding schemes known as ASCII, or American Standard Code for Information Interchange, is the minimum amount of space required to represent one character, such as a letter, a digit, or a symbol. So if you're watching this on a Windows computer right now, you could launch the Notepad application, and you could type in the word hello and save that file, and because there are 5 plain text characters, the file will be 5 bytes in size. So we tend to work in bytes as the minimum size with respect to storage and processing. Now, as for measuring the total storage, again, you do begin with the bit, which is the binary digit, and as we just saw, there are 8 bits to a byte. But again, there are not many instances where we're just dealing with a few bytes or a few characters. So more commonly, we tend to group those bytes together, and it begins with 1024 bytes, or what is also known as the kilobyte. Now, I'm going to come back to this point in just a moment, but kilo is, of course, synonymous with 1000. And notice that it says 1024 over in the left-hand column. Now, this is simply due to the nature of binary. As you count up in binary, you can only increment values that double the previous value. And this comes back again to something like a light switch. If you have a single light switch, you have 2 possibilities, either on or off. But if you have 2 light switches, then there are 4 possibilities, both of them on, both of them off, one on with the other off, then the exact opposite of that. So that can be thought of as 2 to the power of 2 because you have 2 light switches. If you have 3 light switches, that's 2 to the power of 3, which is 8. If you have 4 light switches, that's 2 to the power of 4, which is 16. So as you keep adding another switch or another bit, you always double the previous number. So if you continue this and you go from 16 to 32 to 64 to 128 to 256 to 512, then you end up with 1024 by the time you get into the kilobyte range. So although we use the term kilo to refer to 1000, in binary it's 1024. Then we continue moving up in increments of 1000. So 1 megabyte is effectively 1000 kilobytes. 1 gigabyte is 1000 megabytes. 1 terabyte is 1000 gigabytes, and 1 petabyte is 1000 terabytes. So again, we keep incrementing by 1000. And with respect to the storage devices of today, such as hard drives and solid-state drives, we're generally up and around the low terabyte range. So if you were to go to purchase a new laptop or a desktop computer right now today, you would likely see a hard drive of maybe 1 or 2 terabytes. But of course, you can spend more for larger drives, or you can spend less and get a smaller one. It really just comes down to your needs. Now, I mentioned how I would come back to the sizing in a little more detail, and as we just saw, we talked about the kilobyte, the megabyte, the gigabyte, terabyte, petabyte, and even an exabyte. And the symbols you see are, not surprisingly, KB, MB, GB, TB, PB, and EB. But the way that we use these terms, again, begins with kilo, which refers to 1,000. And if we are going to take that literally, then another way to express that as a decimal value is by using base 10. Okay, in other words, the 10 digits that we all use every day, 0 through 9. So if we are going to treat a kilo as exactly 1,000, then the base 10 value for that is 10 to the power of 3. That's a 1 followed by 3 zeros. That's 1,000. Similarly, a megabyte, if we want to use exactly 1 million, that's 10 to the power of 6. Again, a 1 with 6 zeros. And we just keep going. A gigabyte or a billion is 10 to the 9. A terabyte or a trillion is 10 to the 12. A petabyte is 10 to the 15. And an exabyte is 10 to the 18. So by incrementing by 1,000 each time, the exponent increases by 3 because it's 3 extra zeros each time. But there is another unit of measure that is available, and these do work with the strict binary values of base 2. So what we see here are different terms that are starting to become more common, and they include the kibibyte, the mebibyte, the gibibyte, tebibyte, pebibyte, and exbibyte. Now, the symbols are a little bit different. They include a small I in the symbol, so we see KIB, MIB, GIB, and of course all the rest. But these use the strict base 2 values. So in this case, 2 to the power of 10 is exactly 1,024. So these are quite simply more accurate in terms of terminology. The kibibyte is exactly 2 to the 10, so it's 1,024 bytes. It's not 1,000 bytes. The mebibyte is 2 to the power of 20. The gibibyte is 2 to the power of 30. So now it's the exponent that's incrementing by an even number, but it's going up by 10 each time. Now, these still equate to more or less the same value. Again, in other words, 2 to the power of 20 for the mebibyte is more or less 1 million bytes, which again is what we typically refer to as the megabyte. But these values do express the actual storage more accurately. And the reason for that is because if we look at the kibibyte, the difference between that and a kilobyte is literally only 24 bytes. That's a very small difference. But once you get up into the values of gigabyte versus gibibyte and terabyte versus tebibyte, then the difference becomes quite significant. In fact, the difference between 100 terabytes and 100 tibibytes is a little over 9%. Now, that's a lot because 9% of 100 terabytes is 9 terabytes. So that's a significant difference in terms of the two values. So this, again, is why you are starting to see these values more commonly, because they do more accurately reflect how much storage is actually available, as opposed to just using a more rounded term such as terabyte to refer to 1,000 gigabytes. That just isn't accurate enough anymore. So how much data storage then is needed? Well, it always comes down to the application. And this does not necessarily refer to a software application. It is the application of the storage itself, how it is being implemented and what you're using it for. Now, modern storage solutions do offer immensely more flexibility and more capacity than what we had, let's say, going back 20 or 25 years ago. But particularly with the advent and the proliferation of the internet and its associated services such as cloud storage, the requirements of the technology world in general are growing at astounding rates. So more and more storage is needed literally every day, but technology is able to keep up. But of course, it's a never-ending battle, so to speak. The more we extend the technology, the more we're able to take advantage of it. So we're always sort of pushing the edge of that envelope, so to speak, but that, of course, keeps the technology improving. Now, as for some of the specific storage options that are available, for most of us at home, we tend to use what's known as direct attached storage, meaning that there is a storage device such as a hard drive or a solid-state drive internally in the system. Now, if it's something like a desktop computer, you can certainly have more than one, but something like a laptop is, of course, very limited in space, so you would almost always see only a single device in a laptop. But more advanced solutions include network-attached storage, where the storage is quite literally detached from the systems that are accessing it, and this can allow multiple systems to access that storage at the same time. Now, it's typically still controlled by a single system, such as a network server, but you could have a single network-attached storage device that in fact is managed by more than one server, and of course the content that resides on that storage is available to just about any system that resides in the same network. Then sort of the highest level solution is referred to as the storage area network. Now, this is still detached storage, or it's accessed over the network, but it's a much larger scale. A network-attached storage might just be a single enclosure that has, let's say, 10 hard drives installed. So it has quite high capacity, but it wouldn't be an extremely large device. Storage area networks can house hundreds, even thousands of hard drives, and they definitely are accessed by multiple servers. Any one server is typically allocated a section of the overall space, but you can do that over and over and over again for many different servers so that they are all accessing that same collection of storage, but each one manages its own section independently of the other. Now, these are typically implemented only in very large enterprise-level environments because they are complex and they're expensive, but they offer some of the highest performance and reliability as well. So ultimately, it's always going to come down to your needs, but storage is certainly required in every type of computing environment. It just depends on how you need to implement that storage and what type of applications and services you need. In this video, we'll outline the characteristics of the units used to measure data throughput and bandwidth. Now, we'll begin with throughput, which refers to how much information can be processed in a certain amount of time. Now, in the strictest sense, that is what throughput refers to. It is literally how much information can be processed in a given amount of time. But from our perspective as users, we're typically more concerned with how much time elapses between any given request of an application and how quickly it can respond. And that, of course, largely depends on the throughput, but there are other factors involved. But if you're talking about something like a hard drive, then the throughput is a measure of how much information can be obtained from the disk in a certain amount of time. And the higher the throughput, clearly the faster the device. So as a very quick example, these days, many traditional magnetic hard drives are being replaced with solid-state drives because they quite simply have a much higher throughput, because there are no moving parts such as a spinning disk and a read-write actuator arm. Data can be located and retrieved much more rapidly. So therefore, solid-state drives have a higher throughput. Now, there are other terms involved with throughput, and again, throughput is that measure of how much information can be retrieved within a given time frame, but throughput is almost exclusively used with respect to storage devices. Now, there might be some exceptions, but by and large, it does refer to the capabilities of storage devices. Bandwidth, however, is a similar value in that it does refer to how much information can be passed from one point to another, but bandwidth is almost exclusively used with network traffic, and we'll talk about bandwidth in just a moment. But another term that you might hear is latency, and latency does not refer to how much data can flow. Rather, it is the amount of time that elapses between the beginning of any transfer, or its initial transmission, and the receipt of that data. So it's quite literally a time delay. Now, at the end of the day, that of course has an effect on the speed, as does the amount of throughput or bandwidth, but latency is not concerned with how much data is being moved, simply the time delay between the start and the completion of a transmission. Now, in terms of measuring throughput, perhaps the most common unit of measure is input-output operations per second, or IOPS, and in this case, input-output is treated as one word, so the O of IOPS is in reference to the word operations. And you might also hear transactions per second, but IOPS almost always refers to the device itself. So again, if we are talking about a hard drive, the IOPS value refers to how much data can flow into that device and or come out of that device per second. So in other words, it's how much data can be read from or written to that device per second. Whereas transactions per second usually apply to an application, most commonly database applications. So it's literally how many individual transactions or autonomous units of work can be completed per second. Now, once again, that is going to be dependent on the IOPS value of the storage device being used, but it's not a direct measure of the storage device itself. There are a number of other factors, such as the design of the database itself. So transactions per second can't really be used as an accurate measure of the storage devices, whereas the IOPS value can. Now, some typical throughput measurements that you are likely to encounter will include storage throughput values such as gigabytes per second, and what's important here is that it does express the value in bytes per second. Now, it might not be gigabytes, but that's a very common value for most storage devices in use today. Now, the reason I'm pointing out the bytes per second value is because if we look at network bandwidth, this is measured in bits per second. And what you would see in terms of an equivalent value in this case would be gigabits per second. And it's important to take note here that they do use an uppercase B for storage throughput, so that would indicate the gigabyte per second, whereas with gigabit, it's a lowercase b. So you do need to be on the lookout for those values. Now, that said, again, if you are talking about storage, it is almost always measured in some kind of bytes per second value, whereas network bandwidth is almost always measured in some kind of bits per second value. But it is actually the upper versus lowercase b that makes the difference when it actually comes to documentation. So again, just be on the lookout for the case of the letter B. Now, with respect to network bandwidth, the values that are typically used to express the speed include kilobits per second, megabits per second, gigabits per second, and terabits per second. When I began my career in IT, most networks were running around 10 megabits per second. So that's very slow by today's standards, but it was actually fast back then. Modern networks, including Wi-Fi, can easily reach the gigabit per second speed these days, although we are still in the low gigabit values. But some of the highest level enterprise networks are reaching up into the hundreds of gigabits per second values, so it likely won't be all that long before we start to see terabit per second values. And just for the sake of seeing some actual related values, if we go back to the days of dial-up, or quite literally using phone lines to establish connections, those speeds were measured in kilobits per second, and a fairly low value at that. Only up to around 57.6 kilobits per second can be achieved over a dial-up connection. But around the mid to late 1990s, we did start to see the implementation of things like high-speed internet using methods known as DSL, or digital subscriber line, which went up to 50 megabits per second. So that is a tremendous jump when compared to dial-up. In fact, it's about 1,000 times faster. Then satellite internet, which wasn't used all that often in home environments, but certainly in corporate environments, could go up to about 100 megabits per second when introduced. Cable modems came along, and they could support up into the 100 plus megabits per second range. Cellular, or 5G specifically, can support 1 gigabits per second, Wi-Fi can get up to above 2 gigabits per second, as can fiber optic. And again, we are starting to see speeds that are even above those for more advanced level networks, and it likely won't be long before they're more common even in the home environment. But again, obviously what you want to see is as high a value as possible with respect to both throughput and bandwidth. Clearly, the more data you can transfer within any given time frame, the faster the overall response to any type of application will be. So it goes without saying that faster is better, but of course, faster is also more expensive. So there's always a little bit of a trade-off there. But technology has been improving very rapidly, so these days for most of us, particularly at home, these speeds are more than adequate and very affordable as well. In this presentation, we'll identify the importance of computer troubleshooting, which unfortunately is a necessary skill when it comes to a career in IT, because quite simply, things go wrong. Hardware devices can fail, applications might be poorly developed, and of course there are just things like accidents and various other issues that can arise in an unexpected manner. So troubleshooting is a systematic approach to problem solving, and it typically begins by identifying why something doesn't work, and then of course trying your best to determine a solution that brings it back to a functioning state. Now, that's certainly easier said than done, so when it comes to troubleshooting, you usually need to begin with isolating the problem, and then typically looking for any kind of known issue, which ideally means it's something that you've encountered before, and as such, it makes it a lot easier to fix and typically takes far less time. But the idea of isolating the problem is to try to ensure that you aren't focusing your efforts on something that is not going to yield any results. So, as a very simple example, if a person calls the help desk and says that their computer will not start, but there is power available, then you might have somewhat jokingly heard someone say, well, is it plugged in? Well, that is in fact one of the most common issues. Somebody might have accidentally unplugged the wrong thing, or if the cord is down by the person's feet, it's possible that they just hooked it while they were shuffling their feet and pulled it out. Or if it was plugged into a power bar, maybe they hit the button on the power bar. So you always want to look for those very simple problems first, but isolating also refers to the scope of the problem. In other words, is it just a single person who cannot turn their computer on, or are there several people who have been affected? So if it's several, then there might be a larger issue at hand, but again, the idea is to try to focus in on what the most likely cause of that problem is, as opposed to just making guesses. So that can also involve the ability to describe the problem appropriately, which includes the symptoms that are being experienced, the location and/or the locality, again, how many people are being affected by this problem, the timing with respect to when it occurred, because it might be related to something else that occurred around the same time, the general operating conditions, and the ability to reproduce the problem. So for example, if it is something in an application or in a piece of software that is generating an error, can you dismiss that error, then try to perform that exact same action to see if it produces the exact same error over and over again? This can help you to indicate what the problem might be. For example, if a user is in, let's say, a word processing application and they go to the File menu and they choose one of the most recently accessed documents and they receive an error saying that the document can't be located. If they continually try that and receive the same error over and over again, then perhaps the location of where that document resides is unavailable. So that can give you a better idea as to what the problem might be. Now, when it comes to describing the symptoms, it can help to know where the problem originated, any error codes that might be generated, the manner of failure or the severity, and the overall impact. And again, this might refer to the scope of how many people are affected, or also the level of severity, which comes back to the manner of failure. But the more information you can gather from any given symptom, the more easily you'll be able to identify the problem. The troubleshooting methodology refers to a set process that can generally be followed to try to ensure that you are spending the least amount of time possible in terms of arriving at a solution, and it generally involves gathering information, describing the problem accurately, identifying the most probable cause, developing an action plan based on that probable cause, then performing the fix, assessing the results, which of course is did it work or did it not, and then documenting what you did in either case. So if it did work, clearly you want to document that for future reference. But if it didn't work, you still want to document it so that you don't try the same thing again, or so that someone else does not try the same thing that you have already tried. Typical culprits of problems might include the applications themselves. As mentioned earlier, applications can be poorly developed, so they don't always perform perfectly. And the same goes for the operating systems. Now, these are typically much more thoroughly tested than applications are, but it doesn't mean that the stability and/or the reliability of either an application or the operating system won't go down as the device ages. You can have any number of problems with the device itself that might affect the applications or the operating system, such as problems with the hard drive. If the files cannot be located and loaded correctly, then you could start to develop issues with either of them. Firewalls can often block access to various applications or services. Drivers, which are the instruction sets for your hardware devices, can also cause problems, particularly if the driver is not quite the right one for that device. And this is a little more common than you might think, because in some cases, any given driver might be designed to support multiple different makes or models of the same kind of device, but it might not be the exact correct driver. And of course, servers and various networking components can also experience issues, so the problem might not be with your system, it might be with something that you are trying to access on a network server or through a network device that is failing. And of course, peripherals such as printers, scanners, webcams can all have issues. They're all just hardware devices, and hardware, of course, can fail like anything else. So some useful troubleshooting resources to finish up include web searches and online forums, particularly those that might be found on the vendor's website. And vendors often include troubleshooting guides with their products. For example, if you were to go out and buy something like a new printer, it would probably include documentation that has a troubleshooting section. There might also be a manufacturer's FAQ, or frequently asked questions, section in that documentation or on their website. And of course, third-party experts. If you do have access to someone who knows a little bit more about that particular problem, then by all means consult them whenever you can. Ultimately, troubleshooting is a skill, and the more you do it, the more proficient you will become. But of course, the goal is to spend as little time as possible troubleshooting. So by following these guidelines, you should hopefully be able to spend less time troubleshooting and more time being more productive in other tasks. In this presentation, we'll take a look at implementing proactive measures that can be used in troubleshooting various computer-related problems. Now, that said, you don't always have a choice, so there are effectively two methods of responding to a problem: reactively or proactively. Now, it might be easy to assume that any given person would want to be proactive, but that's not always the case, and it's not always possible. Now, I say it's not always the case because proactive troubleshooting involves identifying problem scenarios before they occur. Now, there can be early warning signs, of course, but being proactive typically involves putting in a little extra work and a little more effort. So not everybody has the initiative to do so. And again, in some cases, it just isn't possible. There might be some kind of issue that occurs that is entirely unexpected or unanticipated, and all you can do is react. Ideally, you just want to reduce those scenarios as much as possible by being as proactive as possible. But as I just mentioned, this does require discipline. You need to try to identify what could go wrong. You need to examine what the circumstances are indicating to you. Where might a problem occur? And clearly, that's not always obvious. You can certainly try to assess the situation as best as possible, but in many cases, it's just not feasible to expect that you can identify every possible problem, nor is it worthwhile to do so. In other words, if you were spending all of your time trying to identify what might possibly go wrong, then you really wouldn't have time for anything else, so you wouldn't be overly productive. But in terms of trying to assess the situation, there is, if you will, a diagnosis toolkit that should begin with a certain level of knowledge. Now, of course, this refers to your own training and your own experience, but it should not be limited to just your own. You should enlist the help of as many others as possible who also have knowledge and experience. Certainly your own skill set, which you should continue to develop over time. The data that is available to you, such as logs or reports, you could go through them to try to indicate where problems have occurred in the past. And of course, the tools that are available to you will also help you to be as proactive as possible. You might be able to identify a number of problems, but if you don't have the tools to prevent them, they're going to happen anyway. And monitoring is also very useful with respect to being proactive, because this is quite simply the process of gathering up information. But this does require a fairly broad approach because, again, you might not know where any given problem is likely to occur. So you would need to gather information from a lot of different sources, particularly if you are in a very large environment. But it's still going to assist in being proactive, because the more information you have at your disposal, the more likely you are to be able to pinpoint where a problem might arise. Then you also need to be alerted to any potential problems, and those alerts themselves also need to be meaningful. You need to be able to understand what's important and what's not. And a common example of this is a process known as auditing, which involves quite literally assessing the activities of users and applications and services in your environment, looking for something that might be suspicious or unauthorized. Now, that in and of itself certainly sounds good, but you can also implement alerts based on what it is that you're auditing. So let's assume that you're attempting to discover if a user is able to access a resource who should not be able to. In that scenario, you might need to track all successful attempts to access that resource. So there could be an awful lot of alerts if you are being informed every single time a person accesses that resource in an authorized manner. So you might get flooded with emails saying that this person successfully accessed that resource, and then this person also did, and so did this person. So you would then have to go through all of those emails to find the potentially unauthorized person who was able to access that resource. So that clearly could be very time-consuming. So you need to figure out some kind of a filtering method that alerts you only when the unauthorized entity succeeds in accessing that resource. So that's just one example, but the general idea is that you do not want to flood yourself with alerts that really don't translate into valuable information. And of course, the ability to diagnose a problem is certainly valuable in troubleshooting, but again, with respect to being proactive, you need to be able to identify the abnormal before it becomes a problem. Now, this will certainly require some expertise and also some experience. You might be an expert in a particular area, but that does not necessarily mean that you have encountered every possible problem. So experience is just as valuable, if not more so, because again, you might be trying to find something that hasn't happened yet. So that certainly can be challenging. Lastly, with respect to being proactive, ultimately it involves taking action prior to a problem occurring so that it does not occur at all, but that in itself involves making the correct decisions. So again, you have to try to assimilate all of this information that we've discussed to ensure that you are focusing your attention on the correct area. There certainly is no harm in taking action that will prevent a problem, but you might end up taking too many actions that could in turn cause problems because maybe you're implementing too many restrictions, interfering with the day-to-day operations of your environment. So being proactive is certainly a balance between taking that action, but also ensuring that they are the correct actions based on the correct decisions. So simply try to do your best to identify what might go wrong, then take whatever actions you can to prevent those, but ensure that those actions themselves do not create more problems. In this presentation, we'll provide an overview of the methods used to identify problems when troubleshooting, which might sound like an easy task, and in some cases, it very well may be. There are certainly instances where the source of a problem is obvious, but that in itself does not necessarily mean that it's an easy fix. But at least you know what's wrong right away. But in many cases, it will require deeper investigation to determine what's happening with a computing device that is encountering problems. So, in those situations where the source of a problem isn't obvious, your investigations should begin by gathering as much information as possible with respect to what the problem is, which itself should include asking questions of the user or users experiencing the issue, and determining if anything has changed since before the problem was detected. For example, if a user reports that an issue has suddenly appeared just after they booted their system in the morning, you might check to see if an update was applied the previous night. So it's important in such cases to gather information from both the user and the device, because of course in this example, the user might only be aware of the problem they're encountering. They might not know how to check for the status of any updates that were applied. So gathering information needs to include all sources of information. But with respect to questioning the user, a technician or a support user needs to be mindful of the fact that standard users might not be overly technical. Therefore, plain language should be used as opposed to any industry jargon, and questions should be direct and to the point, but they should not lay any blame. Even if the user did make a mistake, it was most likely unintentional, so finger pointing simply will not help to resolve the issue at hand. It's certainly fine to educate a user as to how to avoid making the same mistake in the future, but that should also be done in a helpful manner. And even when it comes to asking questions, again, with respect to the fact that users may not be overly technical, initial questions should be open-ended, which allow the user to explain in their own words what they perceive to be the issue. But afterward, you should shift more to closed-ended questions, which typically require a yes or a no answer. For instance, open-ended questions might include, "Can you describe the problem?" or "What happens if you try this?" But closed-ended questions might be, "Were you able to log on?" or "Were you able to open the file?" So typically the answer in those cases would be yes or no. From that point, whatever responses you receive should be documented so that you have a reference, not just for yourself, but for any other technician who might also be involved. This will help to ensure that you don't waste any time and effort repeating the same steps or going back to the user to ask the same questions again. And in many cases, something that has changed is often the source of a problem. So again, it's important to identify if any changes occurred. And as far as a computing device is concerned, of course, that could involve any kind of software or hardware. Operating systems and the applications all regularly update themselves, and while those updates are designed to improve the overall level of reliability, it's by no means out of the question that an update can have the opposite effect. In terms of hardware, perhaps a new printer was added, but an incorrect driver was installed. Or maybe something was physically removed, but a service in support of that device is still running, and it's now generating errors because it's looking for whatever was removed. Changes might also be entirely unrelated to the device itself, such as when a change to the workplace environment is implemented. Perhaps a new wireless networking device was installed, but the existing devices are still trying to connect to the old one. Or maybe some physical maintenance was done to the office, resulting in some cables becoming disconnected. So, regardless of what issue is being experienced, a key factor in being able to properly address that issue and ultimately correct it is being able to identify exactly what the issue is to ensure that you aren't wasting time and energy on aspects that are unrelated to the problem at hand. In this video, we'll describe various methods and approaches for attempting to reproduce a problem when troubleshooting, which provides you with the means to verify that you have correctly established the root cause of a problem. Now, there might be a number of ways by which you can accomplish this, but it will depend on exactly what the problem is. For example, if a user's computer simply won't boot when powered up, that's not really something that you can reproduce on another system. But let's say that a user is unable to access a file on a network server. They might suspect a problem with the server or maybe the network itself. But as the assisting user, if you were able to log in on that same computer with your own identity, then attempt to access the same file, and you're able to successfully access it, then you can dismiss the server and/or the network as the source of the problem. So it might be a security problem or something to do with the user's identity, but even if you can't immediately identify the exact cause, you have already eliminated some probable causes. But using that same example, if you are also unable to access the file with your identity, then you have in fact reproduced the problem. But then you might also try accessing that file from another computer, and if you're successful from that other system, then you've likely isolated the problem to some kind of issue with the user's device. Conversely, if you're still unsuccessful, then you've at least still reproduced the problem on another computer. And you've also likely narrowed down the source of the problem to the server or the network as opposed to the user's device. So the ability to reproduce that problem can be very useful in developing a theory as to what the actual problem is, which in turn provides you with a first step with respect to formulating a strategy to address the issue. Now, as mentioned, in some cases you can't always reproduce the problem, such as when a system simply won't boot. But in such cases, there may still be tools that can be useful in terms of gathering information, which could then be used to test other systems. For example, the BIOS, or Basic Input-Output System of a computer, contains basic settings and configurations for the core hardware of your computer, such as the processor, memory, and storage devices. And each time the computer boots, the BIOS performs a routine check of these components known as the power-on self-test or POST routine. If there are any errors detected during this routine, most systems will produce beep codes to indicate what the problem might be. Now, those codes themselves can vary depending on the make and model, but you can usually verify the beep codes through the product documentation, which should be available online. So let's say the system isn't booting, but it's producing a beep code of 2 long beeps followed by a short one. Now, I'm just making up that code, but you could check the documentation, which might indicate that such a code means that a bootable hard drive could not be located. Given that information, you might just check the cable connection to discover that it has in fact become disconnected. Now, while that isn't a manner of reproducing the problem, you could in fact use another system as long as it has the same type of BIOS, then intentionally disconnect its hard drive and boot it up to see if it generates the same beep code, which is essentially reproducing the error. However, it might not be a matter of a disconnected cable. Perhaps the drive itself has physically failed, but at least you would have narrowed down the probable cause to the hard drive, so you wouldn't have to invest any time and effort looking for other causes. If the system can boot, then another useful tool in Windows-based computers is the Event Viewer or similar logging utilities on other platforms. They simply record events that have occurred on that system, which might immediately reveal the source of a problem. Again, it will depend on what the issue is, but if a user says they suddenly can't print, then of course you could likely try to reproduce that problem by attempting to print from another system. And if successful, then at least you know it's not an issue with the printer. But you could examine the event logs of the problematic system and they might indicate that a driver update failed, so you would immediately know the root cause with no further investigation. Also on Windows-based systems, utilities such as the Task Manager, the Device Manager, and any number of third-party tools can be used to attempt to gain more insight into the root cause of a problem. Task Manager shows detailed information about all running applications and processes on a system, along with their resource consumption. So you might discover an application that has locked the CPU at 100% activity, or one that is causing excessive memory usage and slowing the system to a virtual halt. The Device Manager shows the status of all devices that have been installed and allows you to update, install, uninstall, or roll back drivers to their previous versions. So if, for example, an updated driver for your wireless adapter was released, you might install it simply because it's newer, even if your current driver is working just fine. But if that update in fact causes you to lose your connectivity, then you can revert back to the previously working version without issue. And as mentioned, there are a number of third-party tools that can assist with various types of maintenance and upkeep, and of course to identify the root cause of a problem. Reproducing a problem should also involve determining the scope of a problem. In other words, how many users are being affected. Is it just one, or is it everyone, or any number in between? Toward that end, you should try other systems, at least within the immediate area, to see if the same issue is being encountered, and/or determine if a single procedure or task can reproduce the same issue on each system that is experiencing the same problem. For example, if launching the same application on all systems in the accounting department generates the same error, then you might suspect the server that hosts the financial database. Or if all users in the sales department are receiving the same error message when they first log in the morning, you might suspect that an update was deployed to just those computers. So if you can successfully reproduce those problems yourself, it can most certainly help to at least narrow down the list of probable causes. So whenever possible, your troubleshooting efforts should include an attempt to reproduce whatever problem is being encountered by your users. In this presentation, we'll provide an overview of ways to develop a theory of probable causes when troubleshooting computer issues, which should begin with two basic characteristics. Your theory should be realistic and plausible, and it must also be testable. Now, I'm going to exaggerate for the sake of making a point here, but if, for example, your users arrive in the morning to discover that they're unable to log into their computers, your initial theory should likely not be that all of the servers were somehow stolen overnight. It's just not that realistic, and it's not particularly easy to test or reproduce. Therefore, your theory will not really lead to any productive actions. If, however, you know that building maintenance was performing work during the night, and they were specifically working on the electrical system, then a theory such as a breaker was tripped that cut power to the server room is both realistic and testable, so it would lead to a productive action of verifying that the server room still has power. Even if your theory proves to be incorrect, you have at least eliminated a probable cause, so you can move on to the next. Now, as mentioned, even if your initial theory is both realistic and testable, that doesn't mean that it will be correct. So additional research will often still be required because in some cases, initial theories are nothing more than guesses. Now, guessing in itself is fine at these early stages, but those guesses should at least be backed by evidence or data. So going back to my example of assuming that the server room has lost its power, your additional research should clearly involve visiting the server room to verify if that's the case. And even if you discover that your guess was correct and the server room in fact does not have power, the root cause might not be a tripped breaker. You might go to the breaker panel to discover that the breaker is still on, in which case something else has caused the power loss, such as a primary feed that was accidentally cut during the maintenance. But again, even if you aren't aware of the accidentally cut wire, you've at least eliminated another probable cause by identifying that the breaker is still on. At some point, however, establishing a good theory has to go beyond initial guesses, so you should begin that process by asking questions to all affected users to help determine exactly what the problem is. And those questions should include the very obvious, such as, is the power on? And or have you tried rebooting your system? For as cliche as that might sound, you'd be surprised how many issues can be corrected by a simple reboot. But when obvious questions fail to resolve the issue, then you also have to consider the less obvious and or think outside the box, so to speak, to try to envision the problem in a broader view to ensure that you aren't missing something that could produce results immediately. Toward that end, while your initial guesses might involve the most probable causes, establishing a good theory must also include a list of all possible causes. But again, possible in this context still needs to be within reason. Our stolen servers is technically possible, but rather improbable. Then, from that list of possible causes, you should target the most obvious causes first and simply work your way down that list. Some common examples of possible causes include ensuring that all components have power and that all cable connections are secure, and this can often include many different components depending on the issue. Just as a simple example, if a user is able to successfully boot their computer and use other applications, but they cannot gain access to the internet, then they obviously have power to their device, but their network cable might have become unplugged from the back of it or from the wall. The switch they're plugged into might have lost its power, or maybe the network cable has become disconnected on that end. Other components might include a Wi-Fi access point if it's wireless, the router on the network, a proxy server or other network servers involved with providing internet access, a firewall, or anything else to do with networking, any one of which may have lost its network cable connection or its power. So even problems with an easy solution can sometimes take a while to locate. Other possible causes might include more local issues, such as ensuring that disk and storage devices haven't become corrupted or aren't being accessed properly. Again, these devices have both data and power connections, either one of which could cause a failure if disconnected or damaged, and verifying the configuration of the basic input-output system and or the unified extensible firmware interface, which, by the way, is the successor to BIOS on newer systems, but both of which control the settings of the internal devices of your computer, such as the hard drive and memory, especially if you discover that some recent changes were made to those configurations. Again, much of this is somewhat obvious to state, but the ultimate goal of troubleshooting is to spend as little time as possible chasing down the root cause of an issue. So, by following these guidelines for establishing a theory, it will most certainly assist with accomplishing that goal. In this video, we'll outline some basic methods for testing your theories when troubleshooting and attempting to identify the root cause of a problem. Now, to begin, implementing a test of any theory in itself is really as straightforward as it sounds. Once you have formulated a theory, testing it really is just a matter of taking whatever action is appropriate to that theory. But it's not so much the implementation that is the focus here, rather some guidelines for how those actions should be approached. For instance, any given problem could have a lengthy list of probable and or possible causes. So that list should then be sorted with the easiest and or most likely causes at the top and the more complex and or least likely at the bottom. Then each one should be tested individually in order according to their likelihood, which of course only makes sense, but you might be surprised at how often troubleshooters will jump ahead or just dive in, so to speak, based on hunches or guesses. In addition, when testing a theory, this is not the stage at which you should be looking to make any changes to the problematic device. Testing your theories is effectively still part of the information gathering stage because you're still trying to isolate the root cause by eliminating as many possible causes as you can. Changes should only be made once you have correctly identified the actual root cause. For example, if you only suspect that a system won't boot due to a failed hard drive, you shouldn't just immediately replace that drive. you have to test your theory first by testing the drive itself, which might involve taking it out and connecting it to another computer to see if it can be accessed. If it can, then the drive itself is at least still in a functioning state. There might be other issues, such as corrupted boot files, but just jumping to the point of replacing the hard drive with a new one does not address the root cause. So, if, for example, you do discover missing boot files on that drive when you connect it to another computer, then you have identified a very probable cause, and you could implement a change by copying the boot files from the healthy computer onto the drive that is missing them. Then reconnect it to the original system and verify that it can boot. Now, in this example, that still isn't guaranteed to be the correct issue, or perhaps it's not the only issue, but the actions you took were still appropriate based on the evidence. And while it might seem more than obvious to state, the obvious is where you should begin. Theories of probable causes should always include the most obvious possible causes, and as such, they should be tested first. So be sure to test all cable connections and all power connections, and be mindful that these should include all related devices. For example, if a user can boot but is unable to access a file on a network server, there could be many other components that are disrupting that connection, such as switches, routers, firewalls, Ethernet cables for any of those devices, and of course the server itself. Other somewhat obvious tests of your theories should include verification of the device settings, such as in the system BIOS, particularly if any changes have been recently made, and you should check the status of all boot devices in that system. For example, if the system won't boot, you might suspect that it's an issue with the hard drive, but it could also be a problem with the system's memory, or the processor might have overheated. But if it will boot successfully from a DVD or a USB drive, then you can rule out issues with the memory or the processor. However, if the obvious theories and/or possible causes have been ruled out, then more complex theories might be required, at which point it might be necessary to circle all the way back to step 1, identifying the problem. And you should, in fact, regroup at step 1 to gather as much additional information as possible, because if you assume that some of your initial steps were correct, and you only start over again at, let's say, step 3 of whatever your theory is, you could still be going down the wrong path. Successfully testing a theory should also include documentation of what exactly was done to complete that test, whether that test succeeded in resolving the issue or not, because this will help to ensure that you or others don't repeat the same unsuccessful tasks in the future, saving everyone time and effort. Now, documentation methods and procedures will vary depending on the environment, but the goal of any method should be to construct a knowledge base that acts as a central repository for all documentation, so that anyone in the organization who is troubleshooting any issue can use it as a guide to reduce the amount of time spent on formulating and testing these theories. The one nice feature of troubleshooting is that it's quite likely that any given issue has already been encountered by someone else. So if a solution was discovered, implementing that same solution might save you a significant amount of time. In this presentation, we'll examine how to execute an action plan when troubleshooting computer issues, as well as implementing both corrective and preventative actions. So to begin, before any significant actions are taken against a computer, an important consideration is ensuring that all critical data has been backed up. Now, I'm using the term consideration here intentionally because not every type of problem is going to involve data. For instance, if a subset of users report that they can't seem to access the internet while other users can, then that is most likely an issue with a networking component such as a switch or a wireless access point, a router, or perhaps a network server on their portion of the network, in which case nothing will have to be done to the user's computers. But for a system that won't boot, then it may very well need to have its entire operating system reinstalled, in which case you will almost certainly need to back up any critical data. So again, it will depend on the nature of the problem, of course, but in general, if any significant reconfiguration of a user's device needs to be performed, it never hurts to back it up. For actions that will affect a wider scope of users and/or systems, you might want to consider creating a sandbox environment, which is essentially a staging or a testing area where your changes can be implemented without concern for disrupting normal operations. If successful, then you can apply those same actions to the production environment. And of course, each action taken should be documented along with the results to ensure that if anything does go wrong, it can be more easily pinpointed in the process to help determine what might have caused that problem. Unfortunately, even if you have identified exactly which operations are necessary to correct a problem, it doesn't mean that those actions can be done quickly. So you'll have to take into account any potential downtime, and you should always be prepared to apply patches or updates to both the operating system and the applications on any given device, which in some cases might require several lengthy installations and system reboots. So this might circle right back to being mindful of downtime. And of course, depending on your level of access in the organization, you might need to obtain the necessary permission to be able to perform the required actions. And this might involve both obtaining permission from the end user, particularly if you're working with a device that is personally owned by that user, as well as from a higher level administrator. With your preparations and considerations complete, you're ready to implement your action plan, which might involve actions such as installing and/or uninstalling software, updates, and even the operating system. And in some cases, you might need to edit configuration files, run scripts, or perhaps reconfigure a firewall. Now, of course, those are only a few examples of actions you might take, but in doing so, you should also be mindful of how long those operations would take with respect to the issue at hand, and you should also be prepared to roll those changes back to the state that they were in prior to your actions, so that in the event of a new problem arising, the systems can at least be reverted back to the state they were in, so that you're at least no worse off than you were when you started. Now, just to give you a couple of real-world examples of those two considerations, I've worked in a few different environments where computers could be reset to a default state by applying what's known as an image, which is a file that contains a capture of the state of a system that has been fully configured, complete with all necessary software and drivers already installed, and in these environments, a problematic system could be re-imaged, usually in a matter of only 10 to 15 minutes or even less, depending on various other factors. And from a software perspective, the system would essentially be new. Now, re-imaging can't always be done in every situation, but from the standpoint of time, there would have been very few instances where the general processes of troubleshooting, including gathering data, determining probable and/or possible causes, creating an action plan, and implementing that plan, would have taken less time than re-imaging would. So that's always something to consider. In some cases, a catch-all fix, so to speak, might save you a lot of time, even though you might not have determined the exact cause of the problem. And as for rolling back a system, this will also depend on what the problem is and what kind of system you're working with. For a physical computer running Windows, something like a driver update has a built-in rollback feature right in the Device Manager utility. So if an update was unsuccessful, you can literally just click the rollback button and the updated driver is discarded and the previous one is reinstalled. You can also use a feature in Windows known as restore points, which can take what's referred to as a snapshot of the state of your system prior to making changes, so that if those changes are unsuccessful, you can simply revert back to the restore point you just created and those changes are similarly discarded. Lastly, if you're working with a virtual machine, they have that exact same ability built in, wherein you can take a snapshot, or what's also referred to as a checkpoint of the entire virtual machine, then make as many changes as you like to any aspect of the virtual machine, and once again, if those changes turn out to be problematic, then you simply revert back to the checkpoint, and it's as if nothing ever happened. But for situations when you can't just quickly reimage or just as quickly revert to an earlier state, your action plan should prioritize each action by ease of implementation and by how potentially disruptive each action might be. Possible solutions should be listed in order of how likely they are to address the root cause, and larger action plans should be broken down into smaller, more manageable steps. This way, if any given action fails, you simply move to the next option and continue accordingly. Finally, if your efforts prove to be successful, then before considering the matter closed, you should verify that full functionality has been restored, and when and where possible, you should implement preventative measures to help ensure that the same issue does not occur again. Now, this of course will also depend on the nature of the problem. If, for example, the issue was hardware failure, then there might not be anything you could do to prevent another failure. But if a user was perhaps misinformed about how to perform a particular action, or they simply made an error, then you can certainly inform them as to how to avoid that error in the future. And as always, the entire process should be documented to ensure that you and other troubleshooters can resolve that same issue more quickly and easily should it occur again. In this presentation, we'll take a look at some methods for verifying system functionality during troubleshooting activities, which of course ensures that the root cause has been effectively corrected, but also ensures that your actions have not resulted in any new issues. Now, like many things in troubleshooting, the verification methods you implement will vary depending on the nature of the original problem. And you also can't spend all day ensuring that every single application or service is working. But as an example, if a user reported that they were unable to access the internet, there may have been many other network locations and services that they were also unable to access. But not reaching the internet was their primary concern, so they didn't mention anything beyond that. You might have determined that, in fact, they weren't able to access the network at all due to an incorrect IP address configuration. But as for verification, in this example, you should certainly ensure that internet access has been restored, as well as their email and access to network resources such as printers and folders. Other verification actions should include a complete reboot of the system, which means it should be entirely powered off and back on again. As just mentioned, all network connections and connectivity should be verified, and application functionality should also be checked. Now again, you probably would not have time to verify that every single application on that system can be successfully launched, but certainly any problematic applications should be verified for functionality. And your tests should also include the ability to perform specific functions from within that application, such as the ability to print or to save documents to specific locations. And you should also verify the functionality of any attached devices, such as a printer, external USB devices, or perhaps any Bluetooth connected devices. And of course, you should also ensure that no error messages are being generated, which itself should also include checking the system logs. For example, on a Windows system, the Event Viewer application displays system errors and warnings that have been generated, but many of those are not presented directly to the user. In other words, if you don't check for them yourself, you might entirely miss them, so any verification should include a check of the system logs. In some cases, however, your verification efforts might in fact reveal that there is still a problem, which unfortunately will require you to revisit your original action plan to ensure that you have implemented all steps of the plan. And in some cases, you may have to go all the way back to square one and reconsider the probable cause. In other words, it's entirely possible that you may have only addressed a symptom, but not the root cause. Finally, if your tests do reveal that the root cause has been properly and fully addressed, then the last step should be to implement preventative measures wherever possible to help ensure that the same issue does not reappear. Now, this of course will also depend on the nature of the problem itself, because some failures, such as physical hardware failures, simply can't be prevented. But when it's an issue with user error or simply a lack of familiarity with an application or a process, then you should certainly inform the user as to how they should approach that issue in the future. And you should update any relevant documentation and/or training procedures to ensure the proper information is included. And this is also something that in itself might require some troubleshooting, in that it's not out of the question that previous documentation has simply become out of date due to an application upgrade or an update having been applied. For example, a new feature may have been introduced to an application, or an old feature may have been removed. So in such cases, any associated documentation will also need to be updated. Ultimately, there is always a balance between verifying functionality and ensuring that you aren't wasting time verifying that every single aspect of a system is working. But most notably, it's important that a troubleshooter not just assume that any given action will be successful in resolving an issue. In short, you should always check your work. For our final presentation of this course, we'll provide an overview of how to document your findings during your troubleshooting activities. And when it comes to organizations that are typically larger and/or more structured with their support, for as useful as documentation can be, it's an aspect of troubleshooting that is often overlooked and/or poorly implemented. And in many cases, this is simply due to its potentially time-consuming nature. So it requires a commitment to quality on the part of all support users to be an effective resource. Unfortunately, and I can tell you this from personal experience because I'm guilty of it as well, one of the biggest problems with documentation is that many support users simply feel like they don't need it. And this becomes a bit of a snowballing situation because, like most things, the more experience you gain as a troubleshooter, the more familiar you become with the issues and the problems that occur, and the easier it becomes to correct them. So when you've implemented a fix that does work, and you know that it properly addresses the root cause, documentation tends to fall by the wayside. But for larger teams of support personnel, with new users coming on board often, a proper documentation library can be a very valuable resource, saving the organization as a whole a tremendous amount of time and resources. And it does so because even though any given fix might correct a specific problem, that doesn't mean that the same issue won't occur again. But proper documentation might have noted that an additional step is required to ensure that the same issue does not reoccur. So it can help to prevent future problems. And by its very nature, it can improve efficiency because one aspect of troubleshooting that is almost always consistent is that any given issue is very likely not the first instance of that issue. In other words, it's quite likely that the issue you're dealing with has been dealt with before, in which case you'll have a clear definition of the procedures to correct that issue, and you can go straight to implementing the documented solution and avoid all earlier troubleshooting steps such as gathering information, assembling a list of probable causes, and creating an action plan. Documentation also does not need to be limited to troubleshooting. It can also include preparatory information for responding to emergency and/or disaster situations, which can help to ensure that no critical data is lost. Documentation should also include a thorough inventory of the types of devices and hardware components in use, which can simplify the process of troubleshooting by ensuring that support personnel know where additional resources can be located. For example, if standardized desktop systems from a consistent vendor are being used, then your support teams will likely have some kind of a relationship with that vendor for additional support when needed, and they can also go directly to the manufacturer's website as opposed to having to search random or multiple sites. Not only should it include inventory information, but it should also define the IT environment in terms of layout, infrastructure, network boundaries, as well as boundaries that define who is responsible for what. In other words, if a problem occurs in, let's call it Zone 1, then it's obviously up to a Zone 1 team member to address that issue. Similar to defining the IT environment, documentation should also define the roles in terms of which users are responsible for which tasks and what the chain of command is. For example, if it's a hardware issue, then a software developer is likely not the best candidate for addressing that issue. So the documentation should define who makes the decision for which user is sent and to whom they should report during their activities. Proper documentation can also indicate where any pain points might be, which can refer to any number of potential issues, but in this context, a good example might be purchasing a new system for a user when theirs has failed, while not realizing that you have a perfectly good system in inventory that is not being used, so that system could have been reissued to that user as opposed to purchasing a new one. Documentation also provides the ability to transfer experience to others so that they can learn more quickly and deal with certain issues as easily as those who have more experience. And it can also help to isolate the cause of certain unintended issues, in that maintaining a history of exactly which steps were performed during the troubleshooting activities makes it easier to backtrack and to possibly undo a step that might have caused those additional issues. Lastly, with respect to documenting any steps that were taken during your troubleshooting activities, you should ensure that you don't omit any steps or combine certain actions into a single entry, because those combined steps might not always be appropriate for different types of devices or problems. And along those lines, you should also ensure that all measures taken are recorded, including those that didn't work, to help prevent others, or even yourself, from wasting time and effort by repeating those same steps in the future. So while documentation can sometimes be time-consuming, the amount of time it could ultimately save you and your support teams should more than make up for the difference. So be sure to invest the necessary resources into a proper and thorough documentation repository. So in this course, we've examined basic concepts of data, CPUs, and troubleshooting methods. We did this by exploring characteristics of data and information as assets, an overview of intellectual property, digital products characteristics, and making data-driven business decisions, computer processors, measuring data storage and data throughput, computer troubleshooting, using proactive measures and problem identification and reproduction, and establishing and testing a theory, executing a plan, verifying functionality, and documenting findings. In our next course, we'll move on to explore basic concepts surrounding computer devices and components.